All right, guys. So we're back from the interruption from the Zoom. So as I was saying earlier, that we talk about position vector starting from the origin at 0, 0 on your graph, and it goes to the endpoint where you have the coordinates at that endpoint. And oftentimes when we are referring to that vector, in this case, the vector OB would have the coordinates P and Q. So if we are referring to it in the terms of matrix form, we would write this in the column form where P would be above and Q would be below. So we have the vector would be represented in this way in the column form, P and Q. So this vector would be the vector B, or the vector OB, because it starts at O, so the vector OB. And we would write this little arrow above to show that the arrow starts at O and it ends at B, and it would be in this form, which is P above. So we're using the endpoints as a descriptor for the vector. So O, the position vector OB would be just equal to P above and Q below. All right. Now, if we're talking about this other vector now from O to P, this vector OP, no, not OP, but rather the vector OA. All right, the vector OA here. I'm not even quite sure why we have this vector OA is represented by P. This vector OB is represented by Q. This vector OC represented by R, which is the resultant vector. So the vector OA from O to A, which is labeled P. So whether or not you call it P or you call it OA, you're referring to the same line segment. So you can refer to it by the P, that they give it the name P, or you represent it by the line, starts at O and ends at A. So for the vector OA, starts at O, ends at A, which would be in the column form of the coordinates RS. And remember now, they label this P, so this is also the vector P, capital P. All right, now, when we're talking about adding vectors, in the previous lesson, we say that if we add vectors, we get what we call a resultant vector. We also say that when we add vectors, the addition protocol or the addition algorithm that we form are the procedure that we generally use when we're adding arithmetic, when we're adding numbers. That procedure of adding numbers is not the same thing that we do when we're adding vectors. When we're adding vectors, it's more of combining the overall effect of two or more vectors. So if we say the vector Q plus the vector P, now, if the vector Q plus the vector P is equal to the vector R, now in vector language, this plus sign does not mean the literal add that you're used to. In vector language, that plus sign means together with. So that's how you have to read it when you're dealing with vector. You don't read it as the usual addition symbol. So together with, right? So if you read this in this way, you would say the vector Q together with the vector P. This now would be equivalent to, the equal sign means equivalent to. And what that equivalent to really means, you're saying that if you put the vector P together with the vector Q, or the vector Q together with the vector P, it can give you the same effect or the equivalent effect as a single vector R. That means if you have, let's say that P is a person, let's say that P and Q are two persons, right? So let's say Q is one person and P is another person. And what we are saying, if Q is pulling this vector in terms of force and P pulling this one in terms of force. Now, if you replace P and Q with R would be a single vector that can do the same work as these two vectors P and Q. So in other words, if you get two maga person and weak person pulling, one is Q, one is P, you can get one strong person, which is R, that do the same work as the two of them. Right? So this vector R can replace the vector P and Q. And that's why when we're dealing with vector, we are just saying that the combined effect of the vector Q and the vector P would be the same as a single vector R. Raise your hand if you understand that concept, guys. Right.
So could you go over it, please?
Now, so we are saying that the vector, this line representing a vector.
Yes, sir.
This line representing another vector. But we are saying that if you are using these lines together, let's say that this is something that you're pulling. Let's say you're pulling a box with some rocks. And you have this vector pulling the box with, say, 2 Newton, a force of 2 Newton. And this one
Yes, sir.
box with a force of 3 Newtons.
Yes, sir.
Now, we are saying that instead of using this 2 Newton and this 3 Newton, you could use one force, which is represented by the vector R. So let's say that instead of hiring these two persons, you just hiring one person that can do the same job as the two of them.
Yes, sir.
You're following me, Mr. Lamar?
Yes, sir.
Right. So we are saying that these two vectors that you combine together are the ones that we are adding would be the same as the single one, which is R. So these are combining to give you the same effect as R. We say that R is the resultant vector of these two vectors that you are combining. Now, the vectors that we are combining, we call them component vectors. So if you have this component vector plus this component vector, meaning if you are combining the two of them, the effect of the two of them will be the same effect as just one single vector, which is R. And so in vector addition, when we're adding vectors, remember that the vectors' magnitude are represented by the length of the line, right? So
Yes,
in vectors, we're adding what we're really saying. you have a line that is that represents 3 newtons, and you have another line that represents 2 newtons, what vector could R be that would give the same effects as the 2 and 3 newton? Now, if you just say 2 plus 3 give you 5, that would be wrong based on vectors. So what you would really have to do to get the vector R is to find the actual length of R, because this length would be a length representing a vector. So if this length too represents vector,
But like, how do you know that Q and P equals R?
so as I was saying, it doesn't literally equal R in terms of the arithmetic sum. You follow what I'm saying?
Yes, sir, I get that, but like,
It's not an arithmetic value, but instead is an equivalent value. So in other words, if you are pulling a string and this person pulling a string, then this person R pulling his string in this direction would have an equivalent pulling force as the 2 and 3 combined. But numerically, you wouldn't just add the 2 plus 3 to get R. But because vector is not dealing with adding numerically, it is dealing with what is equivalent. So this length of line would be an equivalent vector for these two. So how do we really add them is by taking this tree and forming the 2 vectors here, the 2 components, the one which is Q and one which is P. These 2 vectors acting from the origin. So in order to get R, what we do, we combine these 2 vectors to form a parallelogram. So this vector here, which is P, you're going to draw a line from the tip of over here, which is the same length of P, and it is going in the same direction of P. So this line and this line would be parallel lines. So they would be equal in length. So this would also be 3, right? And the direction. Now, when you draw the parallelogram, then this line also going to be equal to this line. Now, the reason for drawing a parallelogram is that vectors addition obeys a parallelogram rule that when you construct this into a parallelogram and finding the actual length of this line in the diagonal of the parallelogram, it gives you the equivalent vector. You following, Mr.?
yes, sir.
Right. So for vector addition, we're using what we call the parallelogram law to give the equivalent vector. And we are also using the triangular law to give the equivalent vector. Now, the triangular law and the parallelogram law are really not so different, because when you talk about the triangular law, you're really talking about a triangle, which is a 3-sided figure. And if you look at 1/2 of this parallelogram, you see that you have a triangle. You follow?
Yes, sir.
So you could use the triangle from the parallelogram. So you could just construct a triangle based on how this parallelogram is and calculate this length. Now, if the length of R obeys the length of calculating in triangle, it means that you have to use like Pythagoras' theorem or trigs to find the length of R. So this is saying that if you have a triangle with this side is 2 and this side is 3, and the resultant would be that third line that completes a triangle, then to find this length of R, you would have to apply something that you know from trigonometry. So if you have an angle, say if you have an angle here, say 120 degrees, then maybe you could try some kind of formula that you would have learned from trigonometry to find this side, right? And you could find which law would you, which rule would you, which trigonometry
Sir,
you would use to find R if this is the case.
sine.
No, it would be the cosine rule,
Ah, Jesus.
right? So the
Sir,
sine.
you can repeat when to use cosine,
Alright.
sine, and
So
tangent
cosine
again.
rule, when you use the cosine rule, you must be given two sides, right? So let's say that you are given this side and you're given this side. You are given two sides and you have an angle between the two given sides. So if you're given this angle and you have two sides with that angle between them, this is one of the condition for the cosine rule. Now, how do you use this rule? You use this rule when you're trying to find the third side, which is not given. So let's say that this is a side that you don't know, or you know this side and you know this side.
Yes, sir.
Then you use this in the cosine rule. And how you write the cosine rule, the first part of it starts off with Pythagoras' theorem. So this side that you're trying to find, which is x, you write that it's similar to how you write the hypotenuse in Pythagoras' theorem. So you start off with this unknown side to be side that you're working out. So you write it out just like how you write out Pythagoras' theorem, a squared equal to b squared plus c squared. So you start with this side, say that x squared, and
Yes, sir.
is, let's say that this was a number 3, a equal 3, and this is equal to 4, b equal 4, then you say a squared is equal to 3 squared plus 4 squared, right? So that's the first part of the cosine rule. And then now what you want now, the angle here, if this is the angle, say 30 degrees. Then now here, you're going to minus, and you're always going to have a 2 after the minus. Now these two values that you have on this side, that you have here, you're going to put them beside the 2, but you're multiplying them. So you're going to have 2 times 3 times 4. Remember now you're not using the power when you put in these, you're just using the number, the base. So you
Yes, sir.
times
Yes,
4.
sir.
Right, and out here now, beside that, you're going to times the cos of the angle that is given between them, which is cos 30. And then now you use your calculator and do the calculation of everything on this side. But remember that you're working on multiplication first. So you do the multiplication part with the cos to multiply all that first.
Or indices first, because
Yes. Then you square these. And then you do addition and subtraction afterwards.
yes, sir.
And then now after you've worked out the value on the right hand side, then you find the square root to get it. So x would be the square root of everything that you work out.
Yes, sir.
So that's one
Cosine.
of the cosine rule. All right.
Yes, sir.
Sometimes when you're given all 3 sides, you can use the cosine rule. But when you're given all 3 sides and you're using the cosine rule, it's generally to find an angle. Right? So in this case where you know all 3 sides, you're going to write it in the formula. And generally, if you're given an angle here, that means you want to find this angle between the 2 and the 3. So it means that you would have to write the formula so that the 2 and the 3 is here and the 2 and the 3 is here and the angle between them will be here. And then you use the inverse cos to find the angle. Right? So that's just giving you kind of a what you call it, a recap.
Refreshment. Yes, sir.
Yeah. Right. All right. So what I'm really saying in terms of the parallelogram rules for vector, you really, when you have two components pointing from the origin like this, you want to construct it into a triangle, then you draw a line from the origin to the end, to the other end of the parallelogram. And then you use some method of trig or Pythagoras' theorem to find that line that you draw. This line that you draw in the middle of the parallelogram is the resultant vector line. So by finding the length of this line, you're finding the resultant vector. All right, so that's the idea behind it. So now, so when we're adding vectors, that's how we add vectors. All right, so here now, for instance, if you're adding the vector p plus 2, which is the same thing that I've been doing around here, then in the position vector form, in the column form, you write rs. And so it's the coordinates you're writing in the vertical sense. And so for Q, you write P2. Then now, if you add them in this way, what you would get is the coordinates of R added to the coordinates of P added to the coordinates of Q. And then now the overall effect of this would be the total, right? Now this would now give you the coordinates of the resultant vector. So the coordinates, if you add the two coordinates in the position vector, so you write them in column form first, then you add them, you add in the corresponding coordinates. Remember, if you're adding matrices, you add corresponding values. So the top values you add together, the bottom ones you add together. So the result that you get will be the coordinates for the position vector of the resultant. Now, this is an example. Let's say that you have a vector which is with coordinate 2 and 1. So the vector u with coordinate 2, 1, the vector v with coordinates 1, 3, and you want to find the position vector for the resultant. So these are the component vectors, but when you add them, you would get you would add their x coordinates 2 plus 1, you get 3. Then 1 plus 3, you get 4. Now this would give you the coordinates of the resultant vector. And if you look at this in a graphical sense, this is how it would look. So if you have your x and y coordinates, so you use your horizontal vertical axis. All we are saying, if you find the point of u in terms of coordinates, that means x equal 2 and y equal 1. So if you think in terms of the x-axis, so you have 1, 2. So this is 2. X equal 2, y equal 1. So it means that if 1 here, you draw a line from the origin to that point. So you draw a line from the origin here to that point. Then what you would have is at that end point, your coordinate would be x equal 2 and y equal 1. Now you do the same thing, so that would be for u. You do the same thing for b. You find x equal 1, so 1 is here, and b and y equal 3. So you count going up on the y-axis. So if that is 1, let's say this is 2, and 3 is right here. All right, so for this vector, b, x is equal to 1, and y is equal to 3. So it means that if you draw your point of where these two lines meet, are 2 points, 2 x and y coordinates would meet, then it would be right here. Now remember now that these are the 2 component vectors that you're adding. And so if you add them, so you add the coordinates 2 and 1. So here where you have u equal 2 at the top, b equal 1, you add those 2 for the x values. So 2 plus 1, you get what? 3 in your result. And then below for the y coordinate, 1 plus 3, you get 4. Now, this value that you get when you add them will be the end point for your resultant. So if you had to find x equal 3 and y equal 4 on this graph, in terms of that point, you would actually go x direction in 3 positions. So you have 3 on the x. In the y direction, you're going 4. So this is 3 and you're going 4. Now it means that you draw your dot come right across. So this is 4. And you come across so that it line up with 3. And you draw your dot going all the way up. So this is where the coordinates 3 and 4 will be. Right, so that's the end point. But if when you draw a line now to this end point, you would realize that this end point start from the origin. It would end right there. Now this line is the resultant vector line. So if you were to construct this now into a parallelogram, you would see that if you connect this line here and this line here, you will get a parallelogram, and this would be your resultant in the middle. Now, the resultant would have a coordinate 3, 4, but would that be the magnitude? That would be just the position, that would be just the endpoint of the resultant. And in the position vector form, you write it as 3, 4 in the column form. But this by itself does not give you the magnitude. So to get the magnitude of the resultant, now you have to take the coordinates and plug it in the formula. So you would have 3 squared for the x plus 4 squared for the y. And then you find the square root of that. So 3 is 9, 4, 4 is 16. When you add 9 plus 16, you get 25. So you get square root of 25, you will get 5. So it means that R would be simply equal to a magnitude of 25. And that's how you calculate the magnitude of the resultant vector after you add the component vectors. Any question, guys? Is everyone following so far and understand? Raise your hand. Okay. Now, so remember now, that will only give you the magnitude of the resultant. But remember, you cannot describe a vector by just giving magnitude alone. You need to be able to give what? The direction. Now, to get the direction, what you would do is to, based on that resultant line, you want to now construct. You want to construct this resultant line. You want to construct in the form of a right angle triangle. So you draw a vertical line. And you draw a horizontal line from the origin. Now, this triangle highlighted in green, what we want to do is to actually find the angle. We want to find the angle from here to here to give you the direction. So the direction is really based on the angle that is right here. So call that theta. Now, because this is a right angle triangle, and if we want to find this angle, we can just find the side which is opposite to the angle, which is the height of this, which is 4. And if you find the side which is adjacent to the angle, which is 3, right? So if you're looking at this angle, this is the side opposite and this is the side adjacent. So which of the trig ratio you use opposite and adjacent?
Tangent.
Tangent. And that is always the case. Once you're given an opposite side and an adjacent side, you're using the tangent. So we are saying the tan of the angle theta is equal to the side opposite, which is 4, over the side which is adjacent, which is 3. And then now we divide 4 by 3 with our calculator and then find the tan inverse of that to get your angle. So the angle of theta is really the tan inverse. The tan inverse of 3 over 4. No, 4 over 3 rather. Is that clear, guys? And so when you work that out, you will get an angle of 53.1 degrees. Now this angle is what gives you the direction. Because all that is saying is that this line is going in a direction 53.13 degrees from the horizontal. And that is enough to define a direction for your vector. So this vector then would have a magnitude of 5. And when we say magnitude of 5, we're talking based on whatever unit you are using. But suppose these vectors represented forces, then you would have to use a unit for force, which is newtons. So if these are forces, you would say it have a magnitude of 5 newtons, and it has a direction of 53.1 degrees, right? From the horizontal. If you have a different unit, because sometimes a vector might be like force, it might be velocity. If it is velocity, you know that velocity, the unit for velocity is meters per second, right? So if you're writing meters per second, you can write it like this, or you can write it like this, meters per second, and raised to the -1, all right? So if you're not using newtons and you're using velocity, you would use this unit instead of newtons. Is that clear, guys? Raise your hand. Any question? I'm not getting enough response to be comfortable that you guys are understanding. For those who are not raising your hands, could you ask some questions or something so that I can figure out what it is that you are not clear on? If you're not asking any question and you're not responding, I'm just going to think that everything is okay and then I'm going to move on. Is that okay, guys? Can I move on? Raise your hands. All right. Let us try to look at some questions. All right, here now we are looking at the position vectors. Well, these are, well, not well, yeah, position vector is written in column form. So you have the vector P, which is 2, 3, and the vector Q, which is -1, -1 and +1. Write down as column vector 2 times P. Can anybody do that? What if you're going to write this in the column vector form, what would this be, guys? Anybody? 2P would be equal to what? Guys?
So 2, 3 that 1, 3, so it'll be 2/3 plus.
Remember that you're given P up here now. What is P? This is P.
Yes, sir. 2/3. 2 and 3.
All right, so 2P would be 2 times
Yes, sir.
matrix 2, 3. And remember, you're really dealing in the matrix. You're dealing with matrix. So in matrix, this would be a scalar multiplication. You're multiplying what is in the matrix by numbers outside. Anybody remember how to do that? When you're multiplying a matrix by a number outside, you multiply everything inside by that number. So what would you get in this as a result?
Sir, 4/6.
So you'll get 4/6. So 2P would, in the column vector form, would be 4/6. Is that clear to everyone? Raise your hand. Okay, what about E here? What is negative Q? So Q would be -1 and 1. Negative Q would be negative of the matrix. Now, if you have negative of the matrix, what it really means is that you multiply the matrix by -1. If you multiply that by -1, what you get?
+1 and -1, sir.
All right, so you'll get
Just a six.
+1 from above and -1 from below. All right, so for this one now, C would be half P. What would that be? P is what? 2 and 3. Half P would work out to be what, guys?
One on 1.5.
So it would be 1. And you could write it in a fractional form. So it's just 1 and 3/2. Because remember, if you're multiplying by a half, it's the same as dividing by 2.